Hi, I'm Craig Grimley, working with Agilent Technologies on LTE development. A common theme in modern wireless communications is the use of multi-antenna techniques such as beamforming and spatial multiplexing in order to improve the cell capacity and throughput. A common problem we hear from customers today is the inability to verify, validate, and visualize the signal at the RF antenna. That's why I'm here today. I'd like to introduce to you the Agilent N7109A multi-channel signal analysis solution, along with the 89600 VSA software installed with the TD-LTE measurement application. Together, this solution will solve that problem.
Let's focus on how beamforming and spatial multiplexing are used within 3GPP LTE. LTE defines many downlink transmission modes, which we will only briefly summarize here. Release 8 defines transmission modes 1 through 7, covering SISO, transmit diversity, open loop single user MIMO, closed loop single user MIMO, closed loop multi-user MIMO, rank 1 spatial multiplexing, and single layer beamforming on port 5. Release 9 introduced transmission mode 8, supporting dual layer beamforming on ports 7 and 8. And finally, Release 10 introduced transmission mode 9, supporting up to 8 layer transmissions. For today's discussion, we will focus on transmission modes 7 and 8, which are currently the main development focus for initial TD-LTE market deployments. Now let's summarize the LTE-defined downlink signal processing flow, specifically from a transmission mode 7 and 8 perspective. As with other transmission modes, the PDSEH data transport block information is channel encoded and rate matching applied, producing either one or two code words which are then mapped onto layers. But note that for transmission modes 7 and 8, the pre-coding block is non-codebook based, and so it is left up to the base station to determine the optimum beamforming precoding to apply. This is based on UE feedback and can also be derived from direct measurement of the uplink sounding reference signal. Also note that beamforming precoding can be dynamic and vary on a per subframe and resource block basis to adapt to changing channel conditions. For demodulation purposes, transmission modes 7 and 8 include the mapping of UE-specific reference signal within each PDSEH resource block. It is important to note that the UE reference signals undergo the same beamforming precoding as per the associated PDSEH data. This concept is illustrated on the processing diagram. The beamforming precoding is calculated by the base station to ideally maximize the signal-to-noise ratio observed by the target UE device. But equally, the chosen precoding will attempt to minimize transmission interference to other UE devices within the same or adjacent cells. As well as producing user-specific beam patterns, the base station also has the capability of shaping a desired sector-wide broadcast beam pattern for common control channel content, which is received by all user devices within the cell. This is possible when the number of beamforming antenna elements is greater than the number of configured cell RS ports. LTE defines resource element mappings for each of the following reference signal types: transmission mode 7 single layer UE specific reference signals for port 5, transmission mode 8 dual layer UE specific reference signals for ports 7 and 8, as well as common cell specific reference signals for ports 0 through 3. All these reference signals need to be verified both in terms of baseband correctness and relative magnitude and phase observed at the RF antenna. Let's consider a typical TD-LTE MIMO beamforming transmission mode 7 and 8 test configuration. A typical 8-element physical antenna configuration used within TD-LTE today is shown. It consists of two groups of antenna elements. Each group is cross-polarized at 90 degrees to each other. Antenna group 0 consists of antenna elements 1 through 4, polarized at plus 45 degrees. Antenna group 1 consists of antenna elements 5 through 8, polarized at minus 45 degrees. Each antenna element within a group is spatially separated by approximately half the RF carrier wavelength. This provides a high degree of antenna element correlation within the antenna group, which is good from a beamforming point of view. Since each of the two groups are cross-polarized relative to each other, there is a low correlation between each of the two antenna groups, which is good from a spatial multiplexing point of view. A typical TD-LTE base station is illustrated, comprising of E node B baseband and remote radio head. The remote radio head provides 8 antenna feeds which are connected to an RF antenna calibration coupler unit for test purposes. Note that the base station calibration of the RF antenna is achieved using a dedicated calibration port connection between the remote radio head and the RF antenna calibration coupler. Verification of the base station calibration performance is a very important aspect of beamforming test. The calibration coupler output is typically fed into an RF downlink channel emulator, shown here in an 8x2 configuration to emulate the downlink channel characteristics. The two channel emulator RF outputs are received by the user equipment test device. In our example, the user equipment test device transmits the uplink signal on 2 output ports, which can be connected to an RF uplink channel emulator in a 2x8 configuration to emulate the uplink channel feedback characteristics. Finally, to complete the feedback loop, the 8 RF outputs from the uplink channel emulator are coupled back into the base station's 8 receive antenna ports. A common problem we hear from customers today is the inability to verify and visualize the beamforming signal at the RF antenna. This is important in order to validate base station RF antenna calibration performance, baseband encoded beamforming weighting algorithm correctness, and demodulation of MIMO single and dual layer EVM at the RF antenna. The solution to this problem is the Agilent N7109A multi-channel signal analyzer, along with the 89600 VSA software installed with the TD-LTE measurement application. The N7109A multi-channel signal analyzer can support 8 phase-coherent RF measurement channels, and using appropriate RF splitters and attenuators can easily be integrated into a typical TD-LTE base station test setup as illustrated here. The Agilent 89600 VSA software provides an easy-to-use N7109A correction wizard. This can be used along with an Agilent MXG or ESGC calibration signal source in order to correct for all the RF cabling and connectors used within the measurement setup. This allows direct, corrected measurements of your 8 RF antenna beamforming performance. With the 89600 VSA software plus N7109A multi-channel signal analyzer, we can start by viewing the time-synchronized RF signal capture from all 8 antenna elements. Enabling the 89600 VSA spectrogram feature, we can immediately gain insight into the frequency resource activity. This allows us to quickly build up a picture of per subframe RF activity levels for user-specific resource block scheduling as well as common control channels and signals. Note this feature does not require any demodulation at this point and is a very useful debugging tool when investigating unexpected RF or scheduling issues, especially when those issues impair normal demodulation of the signal. Prior to demodulating the TD-LTE captured signal, we need to configure the 89600 VSA software antenna group parameter with the appropriate number of elements and spacing used to match our physical RF antenna configuration. As mentioned earlier, the beamforming weightings can be changing on an individual resource block basis. Therefore, we may choose to view the UE-specific weighting results on a per resource block basis or, alternatively, per user allocation. The TD-LTE measurement application provides a rich set of demodulation results to help you verify and visualize your MIMO beamforming signals. Available results include IQ constellations, EVM result metrics, detected resource allocations, UE-specific reference signal weights, cell-specific reference signal weights and impairments, and UE-specific and common broadcast antenna beam patterns. Let's take a closer look at some of these result traces. The demodulated IQ constellations are displayed per spatial multiplexing layer and provide a quick visual indication of the signal's modulation quality correctness. The frame summary trace provides access to individual EVM and power metrics associated with each channel and signal type. It also provides a color key for all channel type results, which is reused throughout the VSA traces. The detected allocations trace lets you visualize the resource block allocations for each user-specific transmission, plus resource allocations used by common control channels. Measured UE-specific reference signal weights are presented in table format for each of the 8 antenna elements. Weightings can be evaluated in both magnitude and phase, down to the individual resource block allocations associated with each user transmission. Separate UE-specific reference signal weights traces are available for each spatial multiplexing layer. To help you visualize the beamforming performance, the VSA software also presents the resultant combined beam pattern trace associated with each antenna group. Measured UE-specific reference signal weights from the first 4 input channels are used to compute the antenna group 0 beam pattern trace. This process is repeated for the second 4 input channels to compute the resultant antenna group 1 beam pattern trace. Note that a separate beam pattern trace can be visualized for each resource block associated with each user device. Similar to how the IQ constellation provides a quick visual health check of modulation quality, the antenna group beam pattern trace provides a quick visual health check of beamforming baseband encoding and RF calibration quality. Any identified anomalies can be investigated in detail using the UE-specific weight trace metrics. Channel frequency, magnitude and phase response traces can be viewed simultaneously for all 8 antenna elements, along with the VSA-supported common tracking error trace. The VSA MIMO info trace reports cell-specific reference signal metrics and impairments measured for all 8 antenna elements. Reported metrics include cell RS power, EVM, timing, phase, symbol clock, and frequency error, allowing you to verify the common broadcast beam pattern weightings associated with each antenna element. The VSA software also extracts these relative antenna weightings in order to produce the cell RS-derived sector-wide broadcast beam pattern, shown here in blue. The user-specific and common broadcast beam pattern trace results can be viewed in either IQ polar format or alternatively in log magnitude dB format. Both formats support VSA markers for easy tracking of main lobe peak levels and azimuth locations during live measurement updates. VSA markers can also be used to read out various beam pattern characteristics like null depth, azimuth locations, and main lobe to side lobe levels. A key metric to be verified within TD-LTE beamforming transmissions is beamforming gain. The VSA software has added a new beamforming gain results trace specifically for this purpose. It reports the dB difference between each UE-specific beam pattern and the common cell-specific broadcast beam pattern to produce a beamforming gain trace result for each user allocation. The beamforming gain results can be viewed for each individual resource block associated with each user's allocation. In summary, the Agilent N7100 multi-channel signal analysis solution, along with the 8-9600 VSA software installed with TD-LTE measurement application, provides an 8-channel phase-coherent measurement solution to enable verification of your beamforming signals.
Today's demonstration has shown the power of Agilent's measurement solution to help you visualize your RF antenna beamforming signals for TD-LTE. For more information, please visit the URL below, and thanks for watching.